All right, good morning. So we finished talking yesterday about dependent systems. And dependent systems is when you have an infinite amount of solutions. And we have one more example to cover, like this. So, first of all, this is a 2 by 4 matrix. And r- hopefully, we're at the point, or we can get to the point where we can see that this is guaranteed to give us an infinite amount of solutions. Unless these two rows, remember every row represents an equation, unless these two equations are contradictions of each other, then we're going to have an infinite amount of solutions because we have an x, a y, and a z equals the answer. So we've got three unknowns and two equations. That's too loose. It's bound to be dependent. There's going to be a lot of freedom here. And we can hopefully tell that once we go to our calculator and do RREF, and that will produce this. So what does this mean? Well, that top row tells me that x plus no y's plus no z's is 98. So in other words, x is 98. And then the second line is no x's but 1y minus 2z's equals negative 43. So again, the answer is an order triple x, y, z. X is 98. There's no debate. But y and z are both free. As long as y minus 2z's is negative 43, then you're going to have a solution. So x, y, z. Let's just, maybe it'll help if we just pick, like, let's say x is at 98. Let's have z equal 5. If z equals 5, then, okay, so this is y minus 10 equals negative 43. So y would have to be negative 33 because negative 33 minus 10 is negative 43. So this is one solution, but that's just the solution when z equals 5. I could let z equals 6 and get a different one. And so you see, it all depends on what z is. X is 98 for sure. Z is just z, but y will be negative 43 plus 2z. And I can get that from this equation. I could add 2z to both sides, and then I will know exactly what y equals. Y equals negative 43 plus 2z. So here is the entire solution parameterized. All right, our next section is 6.4. And before we even get there, we have to remember matrix multiplication is not commutative. This is a first for us. Most of the time when we multiply things, it doesn't matter what order we multiply them in. But if you just quickly check in your calculator, these two matrices are the same. And when you multiply them in a different order, you get different answers. Because matrix multiplication, you take the rows of the left matrix times the columns in the right matrix, and those numbers are often not the same. So you get different answers. So order is important when you multiply matrices. This section is about inverses in equations. So 3 times a third equals 1. Well, 1/3 is the same thing as 3, the inverse of 3, the multiplicative inverse of 3. So if you multiply two inverses in the number system, you're going to get 1. And we call 1 the identity. And we call 3 and 3 inverse, these are inverses of each other. Now, these are numbers, so it doesn't matter which order I multiply these in because it's going to get the same result every time. Some matrices have inverses. This one does. If I take this matrix times its inverse, I get this. This is like the number 1. This is the matrix identity element. And it's worth noting you have to reverse it. If I take the inverse first times the regular matrix, I still get the identity matrix. So remember, matrices are not commutative, so you have to show both ways if you want your answer to be the same, the identity. So this is the identity matrix. More about that later. But so if you have a matrix A, if that matrix happens to have an inverse, then if you multiply them, you're going to get I, which is called the identity matrix. Lots of matrices don't have an inverse, so they are called singular. So they're kind of like all by themselves. They don't have a partner. Not all numbers have an inverse, right? You can't take 0 times something and get 1. So 0 does not have an inverse. Matrices, lots of matrices don't have inverses. And if they don't have an inverse, they're called singular. But if they do have an inverse, they're called invertible, and it has to be a square matrix. Only square matrices have an inverse. These are identity matrices are a square matrix where ones are down the diagonal and zeros everywhere else. And they're indicated by a capital I with a subscript. So I3 is a 3 by 3 matrix with ones down the diagonal, zeros everywhere else. So this is like in the matrix world, this is like the number 1. If you multiply two inverses, you're going to get the identity. So how do we even find an inverse? Well, let's take this, for example. I think this was the one we had. Our first slide. So this is a 2 by 2 matrix. So since it's a square matrix, it's possible that it has an inverse. And I know the thing about inverses. If I multiply by the inverse, I'm going to get the identity. So I'm going to multiply these two. And to multiply matrices, I take the rows of the left times the columns of the right. So row 1 times column 1, that's 3 times W plus -1 times Y. Row 1 times column 1 will give me the answer in row 1, column 1, which is 1. And then row 1 times column 2, so 3 -1 times XZ, that will be 3 times X minus 1 times Z. Row 1, column 2 will give me the answer in row 1, column 2, which is 0. And then row 2 times column 1, that gives me the answer in row 2, column 1. And then row 2 times column 2, that gives me the answer in row 2, column 2. Now, I want to find W, X, Y, and Z because that will be the inverse of this. And I've got 4 equations. But this is good news because I got 4 equations and 4 things that I don't know. So there's hope. But notice the first equation, this equation, and this equation both have W and Y. And the other two both have X and Z. So I can create 2 systems and then just solve. If we were trapped in section 5, I'd have to be a little creative. I can multiply the top one by 2, and then this would become -2y, and then I could add them to eliminate. But we have our calculator. We know that RREF will do it for us. I would RREF this matrix, 3, -1, 1, -4, 2, 0 from the coefficients. And then to discover that, okay, W equals 1 and Y equals 2. RREF this, X equals 1/2, Z equals 3/2. And I just put the W, the Y, the X, and the Z in their appropriate spots, and I get the inverse. So W, X, Y, Z tells me about the inverse of my original function. So this was a little bit of a cumbersome way to find the inverse. There is an easier way, but it only works for 2 by 2 matrices. So if you want to find the inverse of a 2 by 2 matrix, then if that matrix is invertible, because remember, many of them are not, then it's going to equal this. First of all, the matrix part, you see the D and the A got switched. The 2 numbers in the corner got switched, D and A, and then B and C stayed where they are, but they just take the opposites of them. So the opposite of B and the opposite of C. So you rearrange the numbers, and then you multiply them by this scalar, 1 over A times D minus B times C. Let's practice. Let's do 2 of these. Let's use that to find the inverse of this. Well, here's the formula. And so this is A and D are 0 and -2. So this is 0 times -2, which is just 0. And then B and C are 3 and 4. So B times C is 12. So I'm multiplying by -1/12. but then the matrix gets mixed around. So this is A, this is D. These two get switched, and 3 and 4 become opposites. And I multiply everything through, and I get negative 1/12 times negative 2 is positive a sixth. Negative 1/12 times negative 3 is this, and so on and so on. So this is the inverse of this matrix. And here's the symbol. You raise it to the negative first. And I could show that by multiplying them out. And if I multiply two inverses, I'm bound to get the identity element, and I do get it. So when I multiply every row by every column, I do get 1, 0, 0, 1. I guess it's debatable whether that's faster than the other one or not. So here, another example, let's find the inverse of this. So if I can rearrange these, but I also have to find this value, this scalar. So A times D, that's 6 times 1. B times C is negative 2 times negative 3. And right here, we should stop because this scalar is undefined. This is not a real number. This is 1 divided by 0. So your conclusion is the original matrix does not have an inverse. It is singular.